Okay, all right. This week we're going to be doing more work with circuits. What we're going to be doing here is figure out how to find the equivalent resistance of a very complicated circuit. And we will take the rules we came up with last week for series and parallel and extend them into the realm of more difficult circuits. After we work through that, we're going to build one, measure its equivalent resistance, and you should do the same thing at home. Okay, last week we found out that if you have two resistors in series, the equivalent resistance is the sum of the two resistances. And if they're in parallel, then we have to take inverses. The inverses add for parallel resistances, which winds up usually meaning that the equivalent resistance is less than either of the two going into it. This week we're going to have a look at doing resistance networks like this. Figuring out, here we have some complicated resistance network. It's made out of 5 different resistors. Some of them are series, some are parallel. How do you figure out the equivalent resistance of this whole mess? And we'll work with that. So how do we do this? The idea is you just start breaking it up into pieces and figuring out equivalent resistance for that. So if we have this network, the smallest piece I can find in here would be, say, right here. These two resistors, D and E, are combined in parallel. And so I know that if I was to replace D and E by some single resistor, I'm going to call that RDE, then the equivalent resistance of RDE would come from the parallel law, which looks like this. The equivalent resistance of RDE equals 1 over RD plus 1 over RE. And once I know that, I can go back to this diagram and just kind of mentally get rid of D and E and replace them with this single resistor that has the same resistance as those two put together. And we just keep doing the same thing over and over. The next level up would be to combine RDE and RC into one. C and RDE are not in parallel, they are in series. So if I want to make RCDE, that's equal to RC plus RDE, where RDE is what came out of that. Once I've got those two combined, I can mentally take those two out, and I will have a single resistor here that replaces those 3. Okay, now we go to the other side, and there are a couple of ways I could go here. The path I'm going to take is to combine A and B, and A and B are in parallel, so I would have 1 over RAB equals 1 over RA plus 1 over RB. And that I can solve for RAB, and I replace A and B by a single resistor, RAB. Now I have just 2 resistors in the whole diagram. These 2 resistors are in parallel, so I can finally come up with the answer 1 over RAB CDE equals 1 over RAB plus 1 over RCDE. And using that, I can find the equivalent resistance of the whole network. Finally, if I know the voltage on this battery and I know the equivalent resistance of the network, I can figure out the current through the whole thing. So that's how you combine resistors into complicated networks. I hope you've noticed that this process can extend almost indefinitely as long as you know how these things are combined. You can keep doing this over and over and over. There are some topologies that don't work with this. There are tricky diagonal connections and things like that that aren't really parallel or serial. And in that case, you have to dig out something called Kirchhoff's rules to analyze the network. That's sort of beyond this course. I suggest you try Wikipedia, which I'm sure has a lovely article about it. So there we go. That's the theory of what we're doing this week. Now let's take a break and come back and do it in practice. Okay, well, here we are back again with the complicated circuit. And I have constructed this thing. I made it as neatly as possible and used up all the wires in the kit. Anyway, here it is. This is resistor A, which is 10 ohms. B, which is 18. We didn't have any 15s in the kit, but 18 is pretty close. C, up here, this little one, is 22. D is 33. That's D. And E over here is also 33. This circuit involves several sets of parallel resistors, and one of which is in series with another resistor. It's fairly complicated. I went through and calculated it with these numbers, which are what's in the book. What actually was available, this one was an 18. So your mileage may vary a little bit. And if you run through all the algebra and figure it all out, I got a value of about 5.5 ohms. Let's see what we get if we actually measure it. If your meter goes to sleep like this and just shows you a 1 in resistance mode, you just kind of tap the leads together and that will wake it up. And so to measure the total resistance of this network, I can measure it across resistor B. I go from there to there, and it flips around for a while, but if I hold it for a while, it winds up around 6.2 or so, which is pretty close to what I predicted. So, yay! Another victory for science. Rah! Okay, that's it for this lab.